Good day, everyone. This is the second part of the fundamentals of big data, and the topic is about parallel processing. So we will explore the fundamental shift in computing that's defined in the last 2 decades. The move from making single processors faster to using many processors like this. We try to cover the core concepts of parallel processing and then deep dive into its most powerful and common forms data industry. So parallel processing is used to increase the computational speed of computer systems by performing multiple data processing operations simultaneously. For example, when an instruction is being executed in ALU, it is available. ALU, that is arithmetic and logical. The next instruction can be read from the memory. So the instruction is being executed in ALU. The next instruction can be read from memory. So the system can have two or more ALUs and be able to execute multiple instructions at the same time. In addition, two or more processing is also used to speed up computer processing capacity and increases with parallel processing, and with it, the cost of the system increases. But technological development has reduced hardware costs to the point where parallel processing methods are economically made possible in the systems. Parallel processing derives from multiple levels of complexity. It is distinguished between parallel and serial operations by the type into the lowest level. So shift registers work one bit at a time in a serial fashion, while parallel registers work simultaneously with all bits of the group. At high levels of complexity, parallel processing derives from having a plurality of functional units that perform separate or similar operations simultaneously. By distributing data among several functional units, parallel processing is installed. As an example, arithmetic shift and logic operations can be divided into three units, and operations are transformed into a teach unit under the supervision of a control unit. One possible method of dividing the execution unit into eight functional units operating in parallel is shown in the figure you can see. So this is the processor with multiple functional units. So it's starting with the floating point, and then just divide, and then the floating point multiply, and floating point add, subtract, and then incremental shift unit, logic unit, integer multiplier, and there is adder and subtractor. So parallel computing is becoming critical as more Internet of Things sensors and endpoints need real-time data. So given how easy it is to get processors and GPUs, that is graphical processing units today, through cloud services, parallel processing is a vital part of any microservice program. So with that said about this parallel processing, let us try to understand the working behind this parallel processing. So in general, parallel processing refers to dividing a task between at least two microprocessors. So the idea is very straightforward. The computer scientist uses specialized software created for the task to break down a complex problem into its component elements. Then they designate a specific processor for each part to complete the entire computing problem. Each processor will have to finish its portion. So let me repeat that. Computer scientists using the specialized software created for the task to break down a complex problem into its component elements. Will they designate a specific processor for each part to complete the entire computing problem? Each processor completes its portion. The software reassembles the data to solve the complex initial challenge. So when processing is done in parallel, a big job is broken down into several smaller jobs, better suited to the number, size, and type of available processing units. After the task is divided, each processor starts working on its part without talking to the others. Instead, they use software to stay in touch with each other and find out how their tasks are going. After all the program parts have been processed, the result is a fully processed program signal. This is true whether the number of processors and tasks and processors were equal when they all finished simultaneously or one after the other. So, on the whole, simply the idea of divide and conquer. So, if you take a huge complex problem, break it down into smaller independent subtasks, and assign each of those subtasks to a separate processing unit. Once all the units have finished their work, you combine their results to get a final solution. This allows you to finish the job in a fraction of the time it would take a single processor. So with that working of the parallel processing, let us see about the different types of parallel processing. The type of computing called single instruction, single data, that is SISD. A single processor is responsible for simultaneously managing a single algorithm as a single data source. Computer organization having a control unit, processing unit, and a memory unit is represented by this SISD, single instruction, single data. It is similar to the current serial computer. Instructions are carried out sequentially by single instruction, single data, which may or may not be capable of parallel processing depending on its configuration. So with that about SISD, one of the types, let's move on to MISD, which is multiple instruction, single data. So multiple processors are standard in computers that use the multiple instruction, single data instruction set. Using several algorithms, all processors share the same input data. Multiple instructions, single data. Computers can simultaneously perform many operations at the same time. As expected, the number of operations is impacted by the number of situations that's available. Computers that use these single instructions, multiple data, which is another type, architecture have multiple processors that carry out identical instructions. So we are talking about single instruction, multiple data. The one previously was multiple instruction, single data. So however, each processor here supplies the instructions with its unique collection of data. So single instruction, multiple data computers apply the same algorithm to several data sets. The single instruction, multiple data architecture has numerous processing components. So another type is multiple instruction, multiple data. So we are seeing single instruction, single data, and multiple instruction, single data, single instruction, multiple data, now finally multiple instruction, multiple data, which is MIMD. So this multiple instruction, multiple data or MIMD computers are characterized by the presence of multiple processors, each capable of independently accepting its instructions. These kind of computers have many processors. Additionally, each CPU draws data from a different data stream and they are capable of running many tasks at this moment. So multiple instructions, multiple data. So another one is single program, multiple data, which is SPMD. Single program, multiple data, which stand a subset of MIMD, that is multiple instruction, multiple data. Although a single program, multiple data computer is constructed similarly to multiple instruction, multiple data, each of its processor is responsible for carrying out the same instructions. So the single program, multiple data is a message passing program used in distributed memory computer systems. Group of separate computers, collectively called nodes, make up a distributed memory computer. So massively parallel processing. The storage structure called massively parallel processing is made up of the coordinated execution of program operations by numerous processors. With each CPU using its operating system and memory, this coordination will be applied to different program sections. So parallel processing or computing. So let's see some examples about this parallel processing. So supercomputers for use in astronomy. The universe revolves slowly and astrophysicists must use computer simulations to examine these phenomena since star collisions, galaxy mergers, and black hole ingestion can take millions of years. Such intricate models also require a lot of computing power. Recent advancements in the understanding of black holes, for instance, were made possible by a parallel supercomputer. So that's about how we use this in astronomy. What about video post-production effects? Several high-budget film releases, such as Brad Pitt's Ad Astra, John Wick's intricately staged assassination operation, depend on parallel processing for post-production special effects. So black magic designs dark and sea results to be among only a few have such production or post-production facilities with GPU accelerated capabilities that's used for this. So these powerful computers carry out state-of-the-art rendering. These techniques, tracing methods, 3D animation and color collection both require this GPU abilities on a regular basis. Then another field is getting precise medical imaging. Medical imaging was one of the first sectors to undergo fundamental transformation due to parallel processing, particularly the GPU for general computing revolution. So there is currently a large body of scientific literature describing how increased computation and bandwidth capacities have resulted in considerable increases in speed and resolution for practically every area of medical imaging, including MRI, CT, X-rays, and optical tomography. Next is another example about desktop and laptops. Intel processors, which run most high-power modern computers, the HP Spectre Folio and HP EliteBook X360s, Intel Core i5 and Core to give 4 processing cores. The HP Z8 among the most efficient workstations in the industry, allowing to handle complex 3D simulations and real-time 8K video resolutions. So with that about the different types of parallel processing and the examples of parallel processing, let us move on to understand what is this data parallelism all about. Data parallelism is a way of performing parallel execution of an application on multiple processes. It focuses on distributing data across different nodes in the parallel execution environment and enabling simultaneous supercomputations on these data across the different computer nodes. This is typically achieved in single instruction, multiple data mode, and can either have a single controller controlling the parallel data operations or multiple threads working in the same way on the individual computers. The idea of data parallelism was brought up by Jeff Dean, styled as parameter averaging. To overcome the problems in data parallelism, task level parallelism was introduced. Independent computation tasks are processed in parallel by using the conditional statements in GPUs. Task level parallelism can act without the help of data parallelism beyond the GPU needs and data parallelism for better efficiency. So, on the whole, this is a way of performing parallel execution of an application on multiple processes. So, let's understand the philosophy here is to break up the data itself. So, let us take you have one program, one set of instructions, and you run it on many processes. The only difference is that each processor is looking at a different piece of the data. This works incredibly well for problems that are embarrassingly parallel, a term for problems where the data can be split up with every little effort or dependency between the chunks. But the task-level parallelism gives more flexibility and computation acceleration to the GPUs. The task parallelism focuses on distributing parallel execution threads across parallel computing nodes. These threads may execute the same or different threads. These threads exchange messages either through shared memory or explicit communication messages as per the parallel algorithm. In the most general case, each of the threads of a task parallel system can be doing completely different tasks but coordinating to solve a specific problem. So let me repeat that. Each of the threads of a task parallel system can be doing completely different tasks but coordinating to solve a specific problem. In the most simplistic case, all threads can be executing the same program and differentiating based on their node IDs to perform any variation in task responsibility. Most common task parallel algorithms follow the master worker model. So we are referring to single master, multiple workers. The master distributes the computation to different workers and other task allocation strategies being followed. MapReduce falls under the category of data parallel SPMD architectures. So data parallelism applications are listed out here. So we're talking about the image and graphics processing. So we are talking about applying filters, rendering scenes. Every pixel can be processed independently, GPU computing, scientific simulation, weather forecasting, molecular dynamics. The world is a grid, and the physics in each grid cell can be calculated in parallel. So big data analytics, that is searching, sorting, and aggregating terabytes of log files or user data, is Hadoop Spark. The machine learning, training neural networks where calculations for each layer, each data batch can be done in parallel. So these are the different ways or different scenarios where data parallelism can be applied. So to wrap up, the move to parallel processing wasn't a choice. It was a necessity driven by physics. Data parallelism is one of the most effective strategies have for tackling the problems involving huge amounts of data, and it powers many of the tools we use today. While it introduces significant complexity, it's the key to solving the next generation of computational problems. So the future of computing is and will continue to be parallel. So we have understood about what is parallel processing and the different types of parallel processing. Along with that, we did see some examples where parallel processing is being implemented. Then we got to understand about what is data parallelism and also some of the scenarios of data parallelism. And finally, we did discuss about the applications of data parallelism. With that said, let's try to identify your level of remembering because this tool MCQs can help you realize or get an idea on to what extent do you understand this specific topic about parallel processing and data parallelism. What we'll do is I'll give you 3 minutes time, these two questions together. So you can go ahead and try and find the options for these two questions and we'll try to verify what extent is it. Okay, so your time starts Yeah. So it's time. 2 minutes is done. So last 1 minute. We just have the answers ready. Start the discussion shortly. Okay. Now let us start the questions and which is right out of these four options. So the first question, who brought up the idea of data parallelism as parameter averaging? So the options are Alan Turing, Grace Hopper, Jeff Dean, John von Neumann. So it's going to be Jeff Dean. It's the person who brought this idea of data parallelism as parameter averaging. Okay, so I hope you got that right. Now let us move on to the next question, which is so they've asked what is the primary purpose of parallel processing in computer systems. So they wanted to know why exactly are we trying to use this parallel processing in computer system. The main reason being there is to reduce the number of instructions executed, to increase the computation speed by performing multiple operations simultaneously, to decrease hardware costs by using fewer components, or to limit the system to only serial operations. So we wanted to obviously get the maximum out of the systems, right? So the primary purpose of the parallel processing is to increase computational speed by performing multiple operations simultaneously. So that should be the answer for this particular question on primary purpose. Yeah. So with that we will conclude this particular topic about parallel processing and data parallelism, where we did discuss about what is parallel processing and different types of parallel processing. We also about the examples of parallel processing, and we did talk about data parallelism and where exactly can we utilize for some applications of data parallelism. We did see some scenarios as well in that. Uh, so this particular slide showcases the reference material for you to then refer where this content was taken from. Refer. So you can try to get additional information from this book, Big Data Analytics for Bali in 2020. And there's a portal which is talking about parallel processing in detail with much more examples. So the portal Spiceworks and Geeks for Geeks can also be referred, which has some detailed information on parallel processing, which should provide you the benefit of getting more details on this particular topic about parallel processing and data parallelism. So hereby, uh, thank you for having this much patience in hearing out this video completely to understand what is this data parallelism and parallel processing. Thank you.